Hello everyone, I'm Paul and today we're solving problem 3440, reschedule meetings for maximum free time 2. This is another medium interval problem and this version is quite tricky, so first I will show you how to solve this visually and then we'll go with the code. So let's start. This problem is very similar to part 1 and here is the description, but basically we are in an event and in this event we have meetings. So we are given two integer arrays, start time and end time, and in this array we have the start and end times for every meeting, and our job is here. We need to return the longest continuous period of free time during the event if we can reschedule at most one meeting. Of course, these meetings are non-overlapping and we can't reschedule a meeting to a time outside the event. And for this, we are also given the event time. Finally, there's one big difference between this problem and the first version, and it's here. In this version, we can change the relative ordering of the meetings. So let's say we have this input. These are the start times, these are the end times, and the time for the event is 10. Here you can see the same visually. The time for the event is 10, and if we take this meeting, for example, this goes from 0 to 1, meaning from start at index 0 to end at index 0. Now here the solution is to reschedule this meeting here. And by doing this, now we have 7 free spaces here. So we return 7. Now let's see what's happening. Here we are checking if we can reschedule this meeting. And we know that here we have 6 spaces. So if we can fit this meeting into some other place that's not adjacent free space, if we can fit this anywhere else, for example here, well, in this case we have 7 free spaces. Now let's say we have another meeting here, and in this case we can't reschedule this one, so here we have at most 6 spaces. So for each meeting, we need to ask ourselves, can we fit this meeting somewhere that's not adjacent free space? So we can't use this. Can we fit this meeting anywhere else? If we are here, this is adjacent space and this is adjacent space. So can we fit this meeting somewhere that's not in the adjacent space? The answer here is no, because our total range goes from 0 to 10. For example, here the adjacent space is only this. So can we fit this meeting somewhere that's not in the adjacent space? The answer is yes, we can fit this meeting somewhere in this free space. So first we'll preprocess a data structure to answer this question at each step. We'll call this available space. And this will be an array of booleans, and this will have the size of the meetings. So we have 3 meetings. Here we have 3 meetings. So this will have a size 3. And for example, the value for the first index will be true, meaning we can fit this meeting somewhere else. We can fit this here. The value for the next index, meaning for this meeting, will be false. Why? Well, because we don't have any free space other than this, and this free space is adjacent to this meeting. And finally, the value for this meeting will be true, meaning we can fit this meeting somewhere else that's not in the adjacent free space. And then we'll just iterate every meeting plus adjacent space. So we start with this and we check if the value for the current meeting is true, meaning we can fit this somewhere else that's not in this range. In this case, we can have this entire range of free space. So the result up to this moment is 7 minus 0, meaning 7. Next, we are iterating this meeting plus adjacent space. So we are iterating all of this. Now the question is this true or false? And it's false, meaning we can't fit this meeting somewhere that's not in this range. So here we need to take this entire range, meaning 9 minus 1, this is 8, and we need to subtract the time for the meeting that we can't avoid here. So we subtract 1 in this case. 8 minus 1 is 7. And the maximum between 7 and 7 is 7, so our result is still this. Finally, we are iterating this meeting, meaning we are taking this range and we check if this is true or false. It's true, meaning we can reschedule this meeting in this free space. So we take 10 minus 8 and this is 2. And 2 is smaller than the result, so we keep 7 as the result. And finally, this is what we return. Now let's say we have this example. These are the start times, these are the end times. The time for the event is 10. So for example, the first meeting happens from 0 up to 1 and so on. Now we will follow the same process here. We will have our array for available space. This is a Boolean array that's initially empty. The result will be initially 0. And we will also have an integer to keep track of the maximum space at each step. We'll call this S. So first we are iterating meetings from left to right. So let's say we have an I pointer here. We are currently at meeting 0. And now we are checking if the time for the current meeting, meaning 1, is smaller or equal to the maximum free time that we have seen to the left up to this point. And 1 is greater than 0, meaning we can't fit this meeting in free time that we have that's before this index and that's not adjacent to this index. So for the moment we put false here. And now we update the maximum space or maximum free time to the space we have here, which is 0. So this is still 0. Now we are here and we are checking if the size of this meeting, meaning 4 minus 2, meaning 2, is smaller or equal to this maximum free time that we have here. And 2 is greater than 0. So here we also put false in this array. And now to the left we have 2 minus 1 free spaces, meaning we have 1 free space. And 1 is greater than our maximum free space, so this is now 1. Now we're here, the size for this meeting is 2 and 2 is greater than the maximum size we have so far before this, which is 1, meaning we can't fit this here. We just don't have enough space here. So here we also put false, and here we have 2 blocks of free space, so we replace our maximum space to 2. Now remember, we were moving the I pointer from left to right and we were keeping track of the maximum space to the left of the I pointer. Now we need to do the opposite. We will iterate this from right to left and we will keep track of free spaces to the right of I. So we start from here and the maximum space to the right of I so far is initially 0. The size of this is 2 and 2 is greater than 0, so we keep false here. Now here we have 2 blocks of free time, so our maximum space so far is 2 and we update I to the next meeting. Now the I pointer is here and we have a meeting of size 2 and 2 equals our maximum size so far that's not adjacent to the current meeting. So what this means is we can fit this meeting here. Here we have exactly 2 blocks of free space. So we can replace this false with a true now. And here we have 2 blocks of space and the maximum space so far is 2, so we keep 2. Now for the last meeting, this has a size of 1 and 1 is smaller than the maximum size so far, which is 2. Remember, we can't use this space, but we can fit this meeting anywhere here or here. So we replace this with true. And the adjacent space to the right here is 1. 1 is smaller than 2, so we keep 2 as the maximum space. So now with this information, we can iterate every meeting plus adjacent spaces. So we start from here and we are checking if this meeting in this array is true or false. In this case it's true, meaning we can reschedule this anywhere here or here. So we can take this entire range in this case. So the result up to this moment is 2. Next we are in this meeting, meaning we take this range. Remember, we take the meeting plus adjacent space and we are checking if the corresponding value in this array is true or false. In this case it's true, meaning we can reschedule this here. So we can take the entire range from 6 up to 1, and 6 minus 1 is 5, and 5 is greater than 2, so we replace this with 5. Now we are at this meeting, meaning we take this range and we check if this is true or false. It's false, meaning we can't reschedule this meeting outside this range. So the current range goes from 10 to 4, so we do 10 minus 4, and we need to subtract the size for this meeting. This meeting goes from 8 to 6, so we do 8 minus 6, and the result for this is 4, meaning we have 1, 2, 3, 4 spaces here. And 4 is smaller than 5, so we keep 5 in the result. So now we reach the end and we return the result, which is 5. Time and space complexity for this approach will be big O of n. Now let's go with the code and hopefully you will get the idea. First we'll say n is the length of the meetings, so we can take start time, for example, and available space is an array with false times n. And now the maximum space, we'll call this S1, is 0. First we'll iterate this from left to right and then we'll go from right to left. You can do this in only one pass, but I think this is more intuitive and the time complexity is the same. So S1 equals 0, and for I in range n, if n time at I minus start time at I is smaller or equal to the maximum space so far, we can set available space at I to true. And now we need to update S1. This will be the maximum among S1 and start time at I minus, and here we can take 0 if I equals 0, else we take n time at I minus 1. And now we will do the same in reverse, so S2 equals 0 and for I in range from n-1 up to -1 in reverse in steps of -1, if end time at I minus start time at I is smaller or equal to S2, meaning to the maximum space to the right so far that's not adjacent to the current meeting, we can set available space at I to true. And now we need to update S2, and this will be the maximum among S2, and here we can say event time if I equals n-1, meaning if we are in the last element, else start time at I plus 1. And here we need to subtract and time at I. Now with this information we can iterate meetings plus adjacent spaces and get the result. So result is initially 0. We need to return this, and in between for I in range n, remember n is the amount of meetings, left is 0 if I is 0, else it's end time at I minus 1, and the right pointer will be event time if I equals n-1, else it's start time at I plus 1. Now we are checking if available space at I. If this is true, this means we can take the entire range. So result is the maximum among the result and right minus left, else, meaning if we can't fit the current meeting somewhere that's not in the free adjacent space, in this case we say result is the maximum among the result, and right minus left minus the size for the current meeting, meaning end time at I minus start time at I. So this is it for the code. I think this is right. Let's submit this and see if it works. As you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.